In the beginning, I'll go through some of the stuff that happened in the morning. So welcome back. So as it was explained in the morning, the Dolgopyat method had nothing to do with fractal uncertainty principle. Well, this lecture is supposed to partly fix that. So I will start by recalling a little bit the setup of transfer operators correspond to convex co-compact hyperbolic surfaces and set up some notation that I will use today and possibly also on Friday. So, so here's the here's the situation. So let's consider a convex co-compact hyperbolic surface. So here I just draw a specific example, but it's really it can be, you know, there are lots of topological options possible. And each of these surfaces you can think of as a quotient of the hyperbolic disk by some group of transformations. So that stuff here, that's the fundamental domain. Now, it turns out that in dimension 2, so for surfaces, you can actually describe all of these things in a very neat way. In some sense, it's an analog of the Teichmüller theory, but for the convex co-compact case. So what you can do is, you can, you know, for me it's going to be convenient instead of thinking about the disk to think about the upper half plane because formulas are simpler. And it turns out that every single convex co-compact hyperbolic surface can be obtained in the following way. You start with a family of disjoint disks centered on the real line. I'm going to call them DJs. And I will often index them. So I'll index them from 1 to 2R. It's always an even number of disks. And I will, to each disk, there will be its corresponding its conjugate disk. So that's just an indexing notation. And then I will take some transformations in a cell to R, so some isometries of the hyperbolic upper half plane, which map the following way. Each transformation maps the complement of the adjoint disk, or of the conjugate disk, to the interior of this disk. So this is opposite to the notation that was used by Frédéric. In fact, the transformations there is a kind of opposite of the transformations that he uses, but it will be quite convenient for me to label them this way. And the, you know, if you take the transformation corresponding to A bar is just the inverse of this transformation. So this is really, for this particular case, it's pictured here. I have my 4 disks, and here I have transformations. For example, the transformation gamma 3 maps this point into this point into this point, and then it just does this. So it's not hard to see that there are transformations like that. And then you just say you take gamma, which is the free group generated by all gamma a's, well, I guess if it's a group, from 1 to R. And then you take the quotient by this group, and you get your surface. Turns out every surface can be obtained that way. And in fact, what you have here is assembly instructions for your surface. You take these disks, you identify their boundaries by these transformations, and then you just patch it together, and here is your convex co-compact hyperbolic surface. And of course, the infinite ends of this surface would correspond to here these places on the real line, because this is really the infinity of the hyperbolic plane. So somehow, somewhere here is my, you know, is my compact part of the surface, and as I go to infinity, that corresponds to really hitting the real line here. Okay, now let me see. I was supposed to say something else. Right. Then let me also talk a little bit more about notation, which will be useful today, and I think I'll have to continue on Friday probably with the Fourier decay property, if, well, if anybody comes to hear that, that is. But what's useful is you can actually compose these transformations. Well, obviously, you know, you're taking the group generated by them, and so you can index elements in this group by words. And so words for me are just this. My W, let's say n, is just the sequence of things like that, where all aj are in the alphabet, and aj is not equal to aj bar is not equal to aj plus 1. That's exactly describes to you what a free group generated by things are. It's just the element shouldn't go next to its inverse if you think about it in group terms. Now, I would often write, there's also some notation I will often use. A goes to B, where this is two words, potentially long. So this will be useful notation later. This is by definition that AN bar is not equal to B1. Okay, so you can concatenate these words and get a reasonable word. And then to each word A corresponds a unique element gamma A in this group gamma, which is just the product. Okay. And then these words can be also used to index smaller and smaller disks. And so that will create this fractal picture that we will eventually study. So if I have any word A, which is not empty, I will denote the disk dA is just gamma A1 ta 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 AN minus 1 of the disk AN. And in general, I will, when I use the letter I, for example, like that, it's just going to be the intersection of whichever disk with the real line. Okay. So it's really just notation. I'm just labeling things on this picture. So for instance, if I want to look at, for example, a disk D1, 2, D1, 3 is not allowed. Where should I place it? I should take disk D2 and map it by gamma 1. Well, the disk D2 is outside of D3, so it will land somewhere here. Will still be a disk because it's, it's a Möbius transformation. So my D1, 2 will end up somewhere here. And so on. So longer words would correspond to smaller and smaller disks. And these disks form a tree. So words naturally form a tree. The parent, you just remove the last element. And then these disks, they naturally form a tree. Namely, this being a word prefix, being prefix of another word is exactly the same as a disk being contained in another disk. And each two disks, either one is contained in the other, or they are not intersecting. So you have this very nice kind of tree of disks or of intervals corresponding to these disks. So again, this is, I have to say the Schottky world is really, really neat. As we'll see in a talk by Michael McGee later today, in higher dimensions, things can get much more messy when you think about limit sets. And then another concept that Frédéric introduced, which is also going to be very useful for us, is the limit set. So I will call it lambda gamma. So this is my limit set. And here, one way to see it from this picture is just take the intersection over all n, the disjoint union over all words of size n, dA. All right, so just think of this tree of disks like that. So here you'd have 3 disks corresponding to words of length 2, and so on. You have smaller and smaller, and this is my lambda gamma. So I will also abuse my notation a little bit. Whenever it's convenient for me, I'll use the upper half plane model, and then lambda gamma will be inside the real line. And occasionally, soon in fact, it will be convenient for me to use the disk model, and then lambda gamma will be a subset of the circle. And I'll just travel between the two without somehow paying too much respect to that fact. Now, one key object that was introduced by Frédéric, which is exactly the same operator. I'll just, since I'm using the opposite notation, it will also look opposite, which is the transfer operator. So where does it act? Let me say D is the union of all disks. So that's a domain in a complex plane. I can consider the, I always want to call it the Hardy space, but it's not. The Bergman space of this disk. Actually, you can use pretty much any holomorphic space, but the Hilbert ones are easier to deal with, which is the L2 of this intersected with holomorphic functions. So it's holomorphic functions which are in L2 there. That's a very nice Hilbert space. And then my transfer operator will act from this Bergman space onto itself. It's well defined for any value of complex parameter S. So that parameter is the same that was in Frédéric's lecture. So here it's really matches. And it's defined the following way. If I have LSF, and I want to compute it at some point. I will write it as a sum, and here, well, my z lies in one of these disks. So let me say my z lies in the disk db. And then I just take a sum over a, which are in the alphabet, which are not equal to b bar. So I'll just denote it like that, this cute arrow here. And then gamma a prime of z to the power s times f of gamma a of z. So that's the same formula. If you really want to be pedantic, of course, you have to note that this thing is positive when z is on the real line. And so the power can actually be defined uniquely in a canonical way. Now, so what happens is, maybe if I go back to this picture, which is unfortunately a bit low, if I had my function f, so let me just draw it here. So if I have my function f, what does happen? So I'll draw 4 disks, but really the theory doesn't care how many disks there are. Okay, this is just for illustration purposes. I drew that particular surface. Now, if I have my function f somewhere here, well, if I want to know, for example, this transfer operator f on d1, well, what do I have to do? Here's d1, d3, d2, d4. I have to map d1 into itself, into this d11. Have to map d2 into d1, some d12, and then I'll have d14 here. And then what I do is I just look at the each point here, z in d1, is mapped into, what am I doing? Oh god, this is so bad. d21 here, d41. That's what I meant, and my mapping goes that way. Wow, that's embarrassing. Anyway, so each point z in this disk, I can map into this disk, into this disk, and into this disk. And then I take the sum of the values with a certain coefficient. And what will happen in my case, I might as well say it, that for me, the real part of S will always be bounded, but the imaginary part of S will be large. It will be equal to 1 over h, where h is the semi-classical parameter. So you should think of this power as really e to the I over h times the log of this guy, if you're on the real line. And so the log is some well-defined function, but because of this large imaginary part, this is going to be really oscillating. So we're adding a bunch of really oscillating prefactors, oscillating at wavelength h, with these values of this function. Now, if you look at this picture, of course, you see that the value of this ls on, for example, on the disk d1 only depends on the values of f on these 3 smaller disks, which are compactly embedded into the original domain. So, for instance, by using the Cauchy integral formula, by just writing it as an Cauchy integral formula, writes a pullback operator, the identity operator, as an integral of rank 1 operators, effectively. You can see that this ls on this Bergman space is trace class.
Just out of curiosity, Frederick was using CK on the integral on the boundary.
Well, then he used C omega, and C omega is effectively the same. He used exactly the same space without specifying it.
Without going to the detail, I just said you take hidden and
Yeah. What I'm about to present, the complex analysis comes in handy in some of the stuff that I'll present, so that's why I'm making this explicit, what spaces I'm using. Of course, it's true that you can also consider. Yes.
DA are the full disks or half disks? What are we talking about?
Here there are full disks. Here I'll just use them as full disks. But you can see that, of course, the behavior here, if I take a large power of the transfer operator, then I see that ls to the power nf will really depend only on the value of f in these tiny disks corresponding to words of length n, which are very close to the real line. So effectively, studying the invertibility of this operator as an operator on this space actually is the same as studying the invertibility of that as an operator on the real line. So you can also consider this as an operator, for example, I is the union, I is the union of all these 4 intervals. It certainly maps, for instance, the space of continuous functions onto itself. It is not trace class there, but the invertibility of this operator and this operator are exactly the same question. So eventually we'll reduce things to the real line, but for some places having this holomorphy helps. Okay, and then what's nice about having trace class operators is that we can take the determinant.
Why did you exclude P3 in your explanation?
Because it's not allowed. Because if I take gamma, whichever one, if I take, so here I took, this was gamma 1, this map was gamma 4, and this map was gamma 2. If I take gamma 3, it's going to map D1 onto the exterior of all of these disks. And so you have to always somehow have this compatibility condition. It's like, you know, I think the way maybe people originally thought of this dynamical system is by associating it with a sort of a Markov chain, but in infinite dimensions. And these disks, it's like you jump from a state to another state. Some jumps are forbidden. So there's a more general setup for that. But here we just, that's what we get. Now, if you look at this determinant.
Excuse me.
Yes?
I'm sorry. Can you get more? Why is trace class?
Why it's trace class? Well, that's a good question. So let's consider the operator on just d whatever 0, which is just the ball of 0, 1, to itself, which is f of z, or t. Tf of z is f of z over 2, let's say. That's basically what we're doing there, right? Because we're using values on strictly smaller subdisk. It's these maps are going to be eventually contracting, but here you really just use the fact that the image of each disk is compactly contained, so it's contained in the interior of each previous disk. Now, what is that? Well, that's 1 over 2 pi I integral, so I'm going to take my disk b of 0, 1, and here's my disk b of 0, 1 half, which is all the values that are needed for this. And then you take this integral gamma, you get I believe something like that. And then you see, if you fix t, that's a rank 1 operator, right? Because it just gives you this function. Well, z over 2, sorry. Right, so there are many more conceptual ways of doing that. That's a stupid way. I just wrote it as an integral of a trace class operator family. But yeah, so yeah, there are many ways to see it, but that's the one that I can do like that. The reproducing kernel, I'll have to remember the formula for that because I don't work that much.
So it's a contraction in the sense, right?
Yes, as long as it maps the domain strictly inside, as long as you can say embed the contour, and that's, yeah, it does have to do with the fact that the Bergman kernel is really, really nice once you get away from the diagonal. So it's trace class. Now, what happens if we compute the determinant? Well, the determinant, there is a computation, and it uses these fixed points of that stuff. It's a really beautiful theorem, but I'll just repeat the answer that Federic gave you. It turns out that this is exactly the Selberg zeta function at S. So you prove that for real part S sufficiently large, where the Selberg zeta function converges. And then this thing is defined everywhere. And so that gives you actually an entire, holomorphic extension of the Selberg zeta function. And then the stuff that happened in the morning was that, maybe I'll write it here, that S is a resonance. So a pole of the meromorphically continued resolvent of the operator is the same as saying Zm of S is equal to 0. So resonances are really the zeros of the Selberg zeta function. And that's the same as saying that this operator is not invertible. For trace class operators for these Fredholm determinants, determinant is 0, exactly the same as operator is not invertible. There's always a Fredholm operator, of course, and so it's in trace class is compact. So that's a really, in my opinion, a really beautiful computation. But anyway, that's what it gives us. Yes. You could, but it's not going to be trace class. So if you want to, this complex analysis sometimes comes in handy, even though it's not strictly speaking necessary. You could get around it. There are ways, and especially with all these new developments with the, very variable order spaces and so on. It's okay. So now let me go to part 2, and this is or circling back to fractal uncertainty principle, I'll show that I'll state that the hyperbolic fractal uncertainty principle implies spectral gap. So I'll have to define both of these. Well, the spectral gap was already defined. So it turns out that for this problem, we need a fractal uncertainty principle that doesn't have the Fourier transform in it. It has a somewhat different transform. So I'll just define it. So I'm going to define the following operator. I call it bchi, or bchi of h. It will act on S1. So again, I think of S1 as either embedded in the complex plane and then the boundary of this disk, or I identify it with the extended real line. And again, I'll just pretend like the two are the same. Okay? So let me call y points on the circle. 2 pi, well, the 2 pi is completely irrelevant. The power, however, is relevant. So it's an integral operator with a highly oscillating kernel, some phase. It's the dy prime. If for those of you on the right, it's just dy prime, what you would expect. And what's happening here is that this is the Euclidean distance between points on the circle, just embedded into C or R2. It's just the Euclidean distance, literally. And then what's chi? Well, chi should be allowed to be taken arbitrarily, but chi is in C infinity of S1 cross S1, and chi will effectively just be a cutoff away from the diagonal. So once you cut off away from the diagonal, what you get is actually a very nice operator, because you can think of it as e to the minus 2 average times the log of that, which is a perfectly nice function. So a microlocal analyst, when looks at that, sees a semi-classical Fourier integral operator. I'm not going to call it that too much today, but that's the, it has a lot of nice structure, which actually it quantizes the scattering relation of the hyperbolic disk. So there is some geometry behind why I chose that specific kernel, why that specific kernel works. But in any case, it's going to be an operator that's bounded on L2 uniformly in H. It's not too hard to show by T-star argument and integration by parts and Schur's lemma. And that's the operator that I'll use. So you should contrast it with the Fourier transform. The Fourier transform was on R, and there was no cutoff. And here we have e to the minus 2i over h, this log. And Fourier transform would be e to the minus I over h if you want the inner product, so the product. So it's just a different phase function. OK. Now let me see. OK. Right, so we already have the limit set. So let me state the theorem. So this theorem is rather fresh. It's actually not posted yet, but I think we finished checking the proof. It's just a little bit busy with the workshop. So haven't finished the introduction yet, basically. It's adjoint with Maciek Zworsky. And here is a theorem. Assume that lambda gamma, this limit set, satisfies hyperbolic fractal uncertainty principle with exponent beta. So I'll define that. So that's the assumption. What does this assumption mean? Well, it looks pretty much like the uncertainty principle, where my fractal set is going to be lambda gamma, and my Fourier transform is replaced by this guy. So here are some quantifiers. So I have to make the proof easier, I will put some quantifiers, which are really all small numbers that can be absorbed by the improvement that you actually get. So you can just make this equal to 0 and this equal to 1, just the proof wouldn't work. And then for each cut of chi, satisfying these conditions there, we have the following bound. If I look at the h to the row neighborhood of the limit set, just multiplication by that, and then I wedge between two of these this operator, I'll look at it at L2 on S1, the usual one, is ch to the beta. So that's actually this theorem actually is correct as stated. I don't think I'm lying anywhere in the statement, even to simplify things. No, I'll explain that. So the statement is, well, let me finish the theorem and then we'll get to that. Then M has an essential spectral gap, but I will just impolitely call it a gap of size, any size smaller than beta, i.e., so that's the conclusion, i.e., the conclusion is actually very simple, namely the number of zeros of the Selberg zeta function in the region for each epsilon bigger than 0, in the region real part s is bigger than 1/2 minus beta plus epsilon is finite. So you have a strip with only finitely many resonances. All right. So that's the statement. OK. Now, so let me talk a little bit about the statement, the conclusion, and the passage from one to the other. Yes, Frédéric?
So if you replace your beacon by just a Fourier transform, classical, it works the same?
Not quite.
Not quite.
Not quite. It's a bit subtle. So I will let me include it into these remarks. So first of all, as was already pointed out, that this theorem, so this was previously proved in my work with George Zal, which goes back, well, the publication is 2016. And the novelty here is that we use a different method, which is much more direct from the transfer operator point of view. And in the work with Zal, this is using somewhat complicated microlocal analysis. So much more along the lines of what Longjin was talking about yesterday. It's really understanding the behavior of the scattering resolvent, understanding localization of resonant states, and then, reducing to that thing using really phase space for microlocal analysis. So today, I want to present a proof that's different. So this more recent proof that's much more primitive. In fact, if you just have a tiny bit of suspension of disbelief, or rather allow me to be sloppy with terms like something is oscillating at frequency no more than something, I can present the whole proof right here, right now, which wouldn't be true with that proof, certainly. Two, but it's really the same theorem. It's literally the same theorem. Two is, well, what are the previous results? So I will draw them here. Perhaps, yeah, I will draw them here like that. So here's my delta, which is the dimension of the limit set. And here's the betas that I can get. So let me talk a little bit about the assumptions, so the FUP. When can one prove this fractal uncertainty principle? Well, what you can do immediately is this line, half minus delta or 0. So that's easy by volume techniques. I'm not going to write that down. But it turns out that the trivial bound here will give you beta equals to 0. And that just corresponds to what people call the Lax-Phillips gap. Trivial or not, but in this framework, once you introduced all of that, it's a trivial statement. The other one, half minus delta, corresponds to the first resonance being at delta. And that's what's known as the Patterson-Sullivan gap. And so that follows, that can follow with an epsilon loss from here by just analyzing the total volume, the volume of the set, and there is some easy bound to do. So that's something that these standard bounds follow from, the standard gaps follow from standard uncertainty principles. Now, what can also be said, and maybe I'll make it here, is that the Jacobson-No conjecture.
So, sorry, so what is
Yes?
the fractal uncertainty principle underlying Lax-Phillips result?
It just says that this operator is bounded. It's bounded, so it's beta is equal to 0. And it's certainly bounded because b chi of h is bounded. So by the way, since the Jacobson-No line was discussed today, the Jacobson-No conjecture corresponds to beta equals 1/2 minus delta over 2 in this language. And so it's this rectangle. So the whole life, you can spend your whole life in this rectangle, sorry, in this triangle, trying to understand what's happening here. And certainly, I have no idea how to prove a fractal uncertainty principle with such a good bound. So no, no idea there. But I can tell you that this heuristic that Federic presented here, it actually has a straightforward translation to the fractal uncertainty principle world. Namely, if you think of this operator as a huge matrix, because there's a lot of intervals of size h to the row, and the oscillations are much. If all the rows or all the columns of this matrix happen to be orthogonal to each other, so it's somehow if waves localized on different frequencies, when restricted to this lambda gamma of h to the row, were still quite orthogonal to each other, you would get that. So it's really, in my opinion, a bit of wishful thinking in the sense that it's this is really the best thing that could happen. So if your lambda gamma looked exactly like a random set, not a random Cantor set, really a random set, then it would be true. But of course, well, it doesn't. And also, it's the upper limit of applicability of that. So you can see that there is an easy lower bound on the norm of this operator, and that corresponds exactly to that. So certainly, whatever this does, it cannot push past that conjecture, which is probably good because whether or not the conjecture is true, I don't think any deeper gap would hold. All right. So what are the positive results known? So this is standard results, some conjecture. The positive results known, so sorry, that's bad. I do it in notes, but that's because I know which B it is. There is this paper with Bourgain, which tells you that beta is bigger than 0. Well, here, delta is always less than 1. So you can always improve over this. In some way, that really depends on the regularity constant, but effectively depends on the choice of the Schottky data. Then there is a paper with Chin, 17, I believe, which tells you that there is some beta, also depending in a somewhat explicit way, but still depends on the surface, which is bigger than half minus delta, and that's Federic didn't mention that, but those improvements are only true when delta is bigger than 0. If delta is equal to 0, you have the hyperbolic cylinder in which nothing can be improved. That's not too hard to see. So it's this part. And you can see that the corresponding spectral gap is exactly, it recovers the result of Federic No from 2005. But it does so using fractal uncertainty principle. And our proof, in fact, I don't think I'll go over it today, but our proof was heavily inspired by Federic's paper. So as far as how far this is from fractal uncertainty principle, I think we were able to actually obtain a proof through this technology using the techniques for this part. We use the techniques that we learned from Federic's paper, so the use of the methods developed originally. And the moral of the story there is that this volume bound corresponds to just doing a triangle inequality on all different pieces of the matrix, and triangle inequality in L2 is really rarely sharp. So that's which is again a similar idea to, to the one underlying Dolgopet type results. So of course, yeah, there are some differences, but the spirit is quite similar. And then there was another paper with Ken, which gave also improvement over this half minus delta, but only depending on the dimension, also when delta is bigger than 0. And so what this tells you is, it's also like somewhere here, but it only depends on the dimension. In fact, it gave something stronger. So I hope to talk about that on Friday in the remaining TBA slot. Namely, it actually gives you Fourier decay for the limit set, which is somewhat unusual. All right. So this is each of these results you can stick into this statement. Now, remark number 3 will be purely oral, since I lost my chalk. Namely, so this is what you can prove, and why would you care about that? Well, it turns out that people care about these gaps for at least 3 different reasons that I'm aware of. So for a PD person like me, this gap, so the size beta, corresponds to the rate of exponential decay of waves, say for the cutoff wave propagator. So it tells you whether, if you have a spectral gap, it tells you that you have fast dispersion of waves on your manifold. So somehow your trapping is weak enough to not prevent waves from traveling out very fast, decaying very rapidly. So that's from a quantum chaos perspective. That's the one that would be interesting for us. This half minus delta is the pressure gap, and so improving over that is also nice. So you improve over somehow a very standard by now pressure gap. The other reason to care about that is because it tells you, this result tells you about exponentially good remainders in prime geodesic theorem. So if you count primitive closed geodesic on your surface, you can get a remainder that would be equal to, well, so your leading term would be e to the delta, the length of geodesic over L, and then your remainder would be e to the minus beta minus this standard gap. So it's a funny way to write it, but anyway, that's what you get. And so for these people, so for people who care about, for applications to remainders in prime geodesic theorem, you really care about this line. So that's why when delta is bigger than a half, this improvement is already rather large just based on the Lax-Phillips gap. So that's why you see people talk about different, what the size of the gap is and which regime is trivial or not trivial, because different people care about improvements over different pieces of that picture. Because it's people coming from different applications who are, these surfaces appear a lot. And then there's a third application, which I'm really not familiar with in any kind of detail, which is also cares about the improvement over that line. And that is for certain choices of surface, and you have to do more. You have to go to congruence covers, but the underlying question is still the spectral gap over this line. You can get better remainders in counting for certain Diophantine problems. You first count group elements, and then for certain surfaces, arithmetic surfaces, this counting would correspond to finding the number of solutions of Diophantine equations. So this is a really number theoretic question, but that's also some part of this question boils down to this high frequency spectral gap. Only some part. There are, of course, lots of other parts which have nothing to do with it. So as you can see, there are three kinds of applications, and that's why there were, you could say 3 separate groups of people, or 2.5 separate groups of people working on this. All right, and that's why the language and the numerology is sometimes different.
Why do you pick this particular BXH?
Why did I pick the chi, or?
No, this y minus y prime to the minus 2.
Well, it's so we'll see it in the proof. There will be acute identity, but that's of course informative or not. It depends on who you ask. This is basically what the scattering operator of the hyperbolic space looks like. If you didn't have a chi and you had some lower order terms, that's the scattering operator of the hyperbolic space. So it's something that's naturally tells you about scattering on the hyperbolic space. And that's the way it comes up in the argument with Zal. From a dynamical point of view, it's an operator, it's a Fourier integral operator that tells you how the stable and unstable leaves intersect each other. So there is a certain geometry there that's encoded in this neat formula. So there is a reason this specific thing comes up. I didn't just make it up. And by the way, to answer Frédéric No's question, so this and this are proved directly for this operator with an arbitrary phase. This one is reduced to the Fourier transform question in a way that I'm not going to explain. All right, so now let me go a bit to the proof. Yeah, so we just gotten through transfer operators, and now I'm proving that. I'm going to be proving this. Just, you see, just as, if you just walked in 5 minutes ago, you could have caught me trying to speculate about applications to number theory, and then I would be toast.
We again already tried that.
Yes. So.
You're saying Riemann next.
Right. Well, maybe he'll do it. I don't know. All right, so let me talk about the proof. So it's really going to be a sketch of the proof. So we'll see a few things, and we'll see where this operator comes up that I just erased and so on. Well, first of all, so if I look at the spectral gap, this is my S. And so I'm not telling you anything about low frequencies. It's really a high frequency result, or finitely many. So here is my 1/2 minus beta, if you want. Then there's my 1/2, preferably here. And I just know that eventually there will be no resonances there. So this is a high frequency question. So I can just, and this the picture is invariant in the flipped up and bottom. So I can just assume the following numerology, where h is very small. So this will be the wavelength at which things will oscillate. And nu can be between 0 and whichever I'm going to take it beta, and I can spare some epsilon, like that, OK? So that's going to be my value of S. I will show this is not a resonance. So I'll show that the Zeltberg zeta function of that is not equal to 0. Well, we can argue by contradiction. So assume not. Then, so this is the point where the argument would differ from the argument with the paper with Josh. The argument with the paper with Zal would say, then there is a resonant state of the Laplacian. It's a solution to the Helmholtz equation with outgoing properties, and let's analyze this solution. Here, I will say that my transfer operator is not invertible. Well, it's a Fractal operator, so what does it mean not invertible? It means it has a kernel. So there exists a U in HD, not 0, such that U is equal to LSU. OK? And so I'll just exclude the existence of such a U. OK, so that's, so it's, you could say, trivial reductions. Now, let me see. So, of course, if this equation is true, then this is also true if you take a power of the transfer operator. Now, what happens if you take a power of the transfer operator? So I'll just rewrite this equation here. Is U of Z is going to be equal to the sum of, well, if you look at this sum, you just iterate. It's like taking longer and longer words. So I'm just going to take sum over words in Wn, which are compatible with B. And then I get gamma prime of Z to the power S, f of gamma A theta of Z, if Z is in the disk B, and B is some element of the alphabet. Right? Oh, there's no F. There's U here. That's the equation. It's it implies this equation. Now I'm going to commit a small lie. So as you can see here, these gamma A's are going to be very contracting. So if you think about gamma A, what does it do? Well, I have this interval IB or disk, but let me just draw the interval. And then gamma A will map it into this very tiny disk, IAB. So if n is very large, the disk is going to be very small. Unfortunately, the length of the disk cannot be approximated well if you just know how long the word is. So I'm going to ignore this issue. And I'm just going to assume, so this is terrible because that's never true, that the size of each of these disks is like h to the rho, where rho is whichever it's very close to 1 for me. So it's this basically h when a is a word of length n. So that's not true. Any person doing transfer operators would hate me for saying that, but for doing things like that. But what happens is instead of taking a straight up power, you have to take a certain adapted power, and this property would still hold, and you can somehow go down these 3 different depths in different places to make all these intervals about the same size. And then what is true, if this thing held, is that the derivative on the interval of interest, so on this interval of interest, is like h to the rho. So this is like h to the rho in size. This is like 1 in size. And so this is really uniformly contracting. It doesn't do anything crazy. Okay, it's not an affine transformation, but it might as well. It's not very far from that. Okay, so if we look at this situation, we see that now we have we have this. All right, now so that was step 1, I suppose. Now let me go up and down and then talk about step 2. So now I'm going to, so my strategy is the following here. I'll look at this big expression and I'll magically, well, not so magically actually, transform it into the right-hand side into this operator in the fractal uncertainty principle applied to something that's supported in a neighborhood of the Libet set. And then I'll be able to use that norm. So that's where my work will be right now. Let's see how this works. So this is, this is a, from where I stand, this is a rather indirect proof because I come from the PD part of the theory. But if you think of these things in terms of transfer operators, that's the most natural proof I think you could get for this passage. So it really depends on who you ask. Yeah. All right, where's my chalk? Okay, here. Now, part 2 is I have to talk a bit about localization or compact micro-localization, which is a scary word, but I'll just bound a range of frequencies in which my function lives. Okay. So how does that work? So I have so here's the claim that I want to show. U lives at frequencies no more than H inverse. So U restricted to the real line. Your holomorphic function is kind of funny which frequencies it lives in. So I will mostly study just this equation on the real line. So I'll go to the reals, and then that's where the contradiction will happen. But I will use this complex property as holomorphic extension property to show that my function on the real line is localized to frequencies which are not very large. Now, from a point of view of that formula there, it is sensible. So even if you look at this equation, let me write it. So this is really just like that. So just one power of the transfer operator. If you look just at this equation, even without taking a power, you see what does this do? Gamma A is contracting, which means that I took the value of my U on a smaller interval, and then I stretched it. So I stretched the support, which means that the frequency should decrease, right? I decrease the frequency by a certain factor. If I didn't have this prefactor, then basically the only function I could hope for is constant. Because when you apply it many times, U has to be invariant under applications, each time your frequency gets reduced. Well, give or take. That's right. And that's where holomorphy will come in. So this is not the literal proof. Yes, that's right. You could have been a delta function. Then good luck with that. Now, this prefactor, however, I should really write it as, well, there is a half minus nu, which we'll use later. But really, it's the oscillating part is like that, times something. This phi is just the log of the derivative. And so this kicks you up in frequency, by frequency about H inverse. And so you have this situation where you have this function, it's preserved on the operation of stretching, contracting it in frequency and then kicking it up. So that you can heuristically see that it should stay all at frequency H inverse, because otherwise, if it was at much higher frequencies, it would be brought down there by repeated applications of that. How do you prove that? Well, there are many ways of proving that, I'm sure. Because people have worked on transfer operators for different things for a very long time. So every school has their own way. So I will use a very primitive way, which is just the following. So I'm going to be completely correct, I'll define the following weight. It's, those of you who like it, this is a pluri-subharmonic weight. And k will be very large, depending just on my surface. And then if I take this weight large enough, then what I see is the following, that if I look at the supremum of the whole disk of LSU, so if U is equal to LSU, this is really the supremum of U, this is bounded by some, but I'll multiply it by this weight. It's going to be bounded, so I'm using this formula, by the supremum over WKU, like that. I can put LSU, like that. So this is just saying that if you look at this transfer operator on this weighted space, it's going to be bounded. And this is just corresponds to the fact that this, you get exponential growth in the complex. So that's not too hard to see why that should be true. But in fact, you don't need to take the supremum over the whole D. You can just take the supremum over the union of disks corresponding to words of length 2, because it was mapped into smaller and smaller disks, right? So it's really U on this whole thing is really estimated by U here. So we have a function, holomorphic function with some weight, which doesn't change anything here. And then we estimated it in terms of it on a smaller set. And then if I look at if here I had my, let's say, just one disk D, and somewhere here was my D2. It's a union of disks, but doesn't matter. And here's my real line. And my weight breaks exactly the real line, so I can do positive and negative half plane separately. I can see that it's going to be bounded by the supremum over the interval I. Well, the weight is 0 there, to some positive constant, times supremum over the whole thing of the bigger interval to 1 minus c. It's just because log of that is subharmonic. And so you can estimate it at each point by integrating like that. And since all points here are far from this part of the boundary, then you win. And then, well, you can see that from here, so this is really, it's a primitive proof, but it's encoding this idea that I had before. The weight, this h comes in the weight, and that will correspond to this. You see that, well, of course, you can divide. And so you see that your function has a so you have a function on the real line, let's say this u, and it has a holomorphic extension to a rather big set in which it's exponentially bounded. Then the usual counter-deformation argument in Paley-Wiener will tell you that the Fourier transform of this u on R is going to be small, let's say all large of h infinity, at psi over h, if psi is sufficiently large. And so that's what I mean by lives at bounded frequencies. So as Stefan said correctly, in order to do this argument I had before, you need to start somewhere, but the holomorph is what starts us here. All right, so that's one part. Now let me erase something here. Let me talk about, talk a little bit more. Let's see, so we got this. So now if we go back to this formula, this is really the key formula that I will study. So we can see that, so I'm going to just write out the terms in this formula. So I will say, I will call VA is going to be gamma A prime of z to the power s times, or x. So I'm just going to the real line now. I'm done with the complex plane at this point. U of gamma A of x. Right, something like that. So that's just the terms that I had there. So there it says that U is the sum of all VAs. And you can also see, by the way, that here I can call this UA or UAB, strictly speaking, where my UAB is just a certain cutoff times U. And the cutoff, if this is my interval IAB, the cutoff lives here. And this is, by the way, h to the rho. Because you only require the, you only use the values of the function on the small interval. Because this value will always be in this interval. So I can put a cutoff for free. And I'll use that later. Now, what we see is the following, that I will write this thing out. So first of all, what's the norm of VA in L2? Well, that's not too hard to compute, so I will spare you the computation. But you can see gamma A has a, you know what the derivative is. It's like h to the rho. And here you have the imaginary part of s tells you, doesn't change anything in absolute value on the real line. And the real part is what will make some change, because it's also like a power of h. Then do a change of variables formula, and then you get, this is where the that's where the real part of s comes up. So that's going to be important. I suppose I should call it really VAB, whatever, because it's x and IB. OK. So that's easy to see just because the derivative is controlled. Now, what you can also see is now, where does this oscillate? So that's the important thing. So we'll analyze it term by term. I claim there will be 4 terms here. Well, you only see 2. But this one, I'll rewrite it. So you can see that UAB, well, of gamma A of x, this is frequencies no more than h to the rho minus 1. So rather low frequencies. Why? Because I took something that oscillates at frequencies h inverse. This cutoff doesn't change it because h to the rho size cutoff, so that's compatible. And then I stretch the support by h to the rho. And so when I stretch the support, the frequencies at which it lies are going to be here. So it's basically bounded frequency. Not quite, but almost bounded frequency. Okay? So there's that. Now, if I look at this, so this is really, I wrote my u as a sum of bounded frequency things. So each of them lies in this very small frequency band, but times these phase factors. And the phase factors is what we have to analyze. Now, if we analyze, how do we analyze these phase factors? So here's a cute identity. If you like cute identities for hyperbolic geometry, now is now's your time to get excited. But so it's quite a. So I'm just going to fix some point x0, which is let me do that. Fix x0, which is an r and not in any of these intervals, just some base point. And then I will say ya is going to be, by definition, gamma a inverse of x0. And you can check that it lies in the interval ia bar. So by this mapping property, this point, it will be mapped. The first application of this map will map it into, the first group element will map it into one of the 4 or whatever disks. And then it will be mapped more and more. And it will end up in this very, very small interval. Now, here's the identity. Just write gamma a of x minus gamma a of ya squared is equal to x minus ya squared times gamma a prime of x times gamma a prime of ya. OK? Now, let's look at the terms here. This is what we want, right? That's the phase factor that we had there. This is all a's. This is large. Yes, these are all a's. In the paper, they are bold-face a's, but it's hard for me to draw bold-face on the board. Right, that's a true identity. And now, this is what we want, right? That's the term that we want. Let's take everything to the power s. Yep, that's true only for Möbius transformations. So it's a kind of particular proof, but it's quite short because it takes advantage, I guess, of all of these. The proof with Josh, the proof in this paper with Zal was much longer, and you could say from a SPD point of view more conceptual. This one is a kind of a quick, cute proof, but using a lot the hyperbolic geometry. Now let's look how and where does this oscillate. Let's look at this guy. Gamma a of x. Where is that? X is in my interval, so gamma a of x, this is really in IAB, so this is interval of size h to the rho. Right? It's really in this tiny, tiny interval. So the variability here is like h to the rho. This is a constant. This is really x0, so that's far from everything. And then you're taking it to the power, it's like I over h. So if I change my x in an interval of size 1, this changes by about h to the rho. And so you're taking something that can vary on the scale of h to the rho, and then you take it to the power 1 over h. So this is at frequencies also no more than h to the rho minus 1. So that thing doesn't vary much. Yeah, this term doesn't vary much. This is fixed, and then your x, when you change your x a bit, it only changes by a tiny bit. You take it to a huge power, but it changes also by a very small amount. If rho was 1, it would just oscillate bounded frequency. Now, if I look at this term, that's the term that we want. Well, that's the term that we want, and that's the term that we'll get. So that one I'll keep. So that one oscillates a lot. Because, of course, here my x is in an interval of fixed size, and then I take it to this large power, so that varies a lot. And if I look at this guy, this is also at frequencies no more than h to the rho minus 1. So rather low frequency. And the reason is because ya is also in this tiny, tiny interval. So the derivative is not going to change much. So my y, well, actually this is a constant. So that's at frequency 0 as far as the function of x goes. Yes?
That term x minus ya to the 2x, is this the reason why you have bxh of?
Yeah. That's what I'm getting at, that each of these terms, so I wrote u is equal to sum of VAB, where each VAB is equal to absolute value of x minus ya bar, minus ya bar, yes, to the 2s. So this should be well, it's ya, but it's really an ia bar times something at frequencies no more than h to the 1 minus rho, rho minus 1. And if you go back to that operator over there, which I erased, then you see that's exactly the integral kernel that we had there. So you can actually write VAB of x as this operator. So that's the part that needs a bit of work, but it's like Fourier inversion formula. If you had something that oscillates at frequencies no more than 10, you can write it as a Fourier transform of something supported in minus 10, 10. That's what I'm doing, except instead of my Fourier transform, I have this times some WAB, where the support of WAB is in this IA bar, basically. Well, it's quite close to this. You know, this already has size h to the rho, so I can just ignore. Or if you want, h to the rho neighborhood of that. And the norm of this WAB is like the norm of VAB, and that's bounded by CH to the minus rho nu norm UAB. Now, if you allow me one more minute, I am ready for endgame. So once we write all of that down, we see the following. So it's a string of inequalities, and each of them uses something that we had before. So if I look at sum of UAB, so I have these pieces of my function on these small intervals. So I have this big function on this disk, but then I restrict it to each of the small intervals, squared the 1/2. This is L2, AB, like that. So this is like, well, where does it live? The union of all these intervals is a small neighborhood of the limit set. That's how we chose them. They're small intervals. Each contains a point in the limit set. And so this is really U in L2. Right? So I just care for my thing on the limit set here. Then I can keep writing this for a tiny bit longer. I write my U as sum of these guys. And then let me just say W is the sum of WABs. So that's really like that. But my W that I cooked, because of the support property, it again lives near the limit set. So, and now you see where this is going, because here the fractal uncertainty principle comes in. And then you get the norm of W in L2. Well, W in L2, again, it's a sum of disjoint things. So this is like the sum of WAB norm in L2. But each of these guys was obtained. This is really what I'm doing is I'm describing long-time wave propagation in terms of symbolic dynamics. I split it into pieces, and then each piece is transported to another piece, and then I'm reparametrizing. And here, if I look at the norm, I get this minus rho nu. That's how they varied. UAB in L2, 1/2. And then, well, to avoid complete lies, you also get a very small remainder. And then if you stare at this formula, I assume that my nu is less than beta minus 2 epsilon. And then you see this is very quickly decaying. And this thing goes to 0 as h goes to 0. So you wrote u, this norm, you bounded it by itself times a small number. So this means that this norm is 0. And of course, well, one way to say it is that this is real analytic. So use identically 0. That finishes the proof. So I should say 2 organizational comments. So one, I was going originally to talk about this work with Bourgain on Fourier decay. And if there are no objections, I will talk about that on Friday. So unless we find better things to do, which might as well happen. And secondly, I didn't ask Frédéric No's consent for that. So that might change. But I propose to everybody, including Frédéric, that tomorrow, so I reserved the room, that's what I'm saying. Tomorrow at 2 p.m., this is No's talk, volume 2. Again, I couldn't catch Frédéric between here and then, so maybe nothing will happen. I'll email you if not. But it will be more of an informal discussion, as insisted by Federic, rather than an official talk, but it will continue on somehow. You can come and ask questions about Dolgopyat's method, and hopefully Federic will be available. Is that okay?
Your talk on Friday is at 10:30.
11.
11.
Yes. So that one I'll email. So is that okay, Federic? Okay. So it will be more on Dolgopyat's method. And all right, thank you so much, and so sorry so much for running over.